Before I talk about the Bessel functions, I have to talk about the gamma function, because in the general solution, the general power series solution of the Bessel functions, you have the gamma function inside, and you will be lost if you don't know what gamma function is. Well, gamma function is defined as this integral. And of course, if you integrate away the t, it will be a value that depends on the value of x, right? So that value is called a gamma function. In order to understand what this thing is doing, let's first think about what gamma of 1 would be. Gamma of 1 would be integral from 0 to infinity of t to the 0th power e to the negative t dt. And we know t to the 0th power is just 1, so if you integrate this as negative e to the negative t, and you plug in infinity and 0. If you plug in infinity, what's e to the negative infinity? E to the negative infinity?
0.
0. Minus of e to the 0th power, and e to the 0th power is 1, so 1. So gamma of 1 is 1. Now how do we do gamma of 2? Well, you don't. Instead, you just come up with a general formula between gamma of x and gamma of x minus 1 by doing integration by parts. So let's take this formula and perform integration by parts by first integrating with respect to e to the negative t, which gives me e to the negative of e to the negative t. This doesn't change. And here we're going to assume that x is bigger than 1, so that when you plug in 0, it doesn't give you a singularity, but rather it will give you 0, right? If you plug in 0 here, 0 to any power, where power is bigger than 1, it will be 0. And if you plug in infinity, e to the negative infinity is 0, so this part will be just 0. Okay? And then minus of integral from 0 to infinity of see, this one is something that you didn't integrate, so that one, the integration by parts formula says in the next stage, the one that you did not integrate should be differentiated. And this is differentiated as a function of t, because it's an integral with respect to t. So you differentiate using the power rule, which means x minus 1 will climb down. So it will be negative x minus 1. And then you subtract 1 off of this, is x minus 2 e to the negative t dt. And then, as I said, this is just 0. Negative of negative is positive. And look, x minus 1, although this looks like a function, in view of the integral dt, this is considered as a constant because this doesn't have any t there. So this x minus 1 can be brought outside. Is that okay? So we're going to bring the x minus 1 outside. And then look closely what this is. So if this is gamma of x, what would this be equal to? Well, here's the hint. It's x minus 1 times 0 to infinity of t of x minus 1 minus 1 e to the negative t dt. Right? So this, if you write it like this, then this one looks exactly like this one, except x has been replaced by x minus 1. Right? X, if you replace this x by x minus 1, you get this integral, right? So this integral must be 1. No. That's not what I'm saying. It must be gamma of x minus 1. Yes, that's what I wanted. It's gamma of x minus 1. Okay. So along with the result that gamma of 1 is 1, we can immediately use this to find the other value of gamma. So gamma of 1 is 1, and then now we have gamma of 2. According to this formula, it's 1 times gamma of 1. Right? What is gamma of 2? Gamma of 2 is 2 minus 1 times gamma of 2 minus 1. 2 minus 1 is 1, so gamma of 2 is 1 times gamma of 1, so it must be 1 as well. Okay, let me see if you understood. Gamma of 3 is what? 2 times gamma of 2, but gamma of 2 is 1, so you get 2. Right. What's gamma of 4? 3 times gamma of 3. What's gamma of 3?
6.
Yeah, so it'll be 6. Oh, this looks like something. What is it? Huh? Factorial, right. So once you do these, you kind of have an idea what the gamma function is doing. The gamma function is doing the following. You have let's see, gamma of n is same as, see, this is 3 factorial, right? So if gamma of 4 gives you 3 factorial, right? Gamma of 3 gives you 2 factorial. So gamma of n is same as n minus 1 factorial. Or put it in another way, you can replace your n factorial as gamma of n plus 1. Now, the immediate question would be, why would anyone want to do this? We like factorials, it's easy, right? Why would you change something that's easy into something that looks horrible? Well, the reason is when you plug in those series solutions, often you get something times something which is 1 less than the previous one, and then 1 less than the previous one. You keep doing that, right? And it's, at the end of the day, it's multiple of some initial thing, like A4, A0, or whatever, right? So there are cases where you need not only the factorial version for the integers, but also something that behaves like a factorial for non-integer case. So, say for example, if you have 7 over 2, and then you realize that if you solve the series, it's like 7 over 2 times 5 over 2 times 3 over 2. What are you going to call this? You don't, and it's times some A0. Right? What do you call this? Often, you don't need the exact values, but you just have relationship between the coefficients in such a format, right? And that's exactly what happens when you try to solve Bessel's equation. You get these things. And, well, for the odd case, I talked about this double factorial thing, right? You've seen double factorial thing. But that's not always possible. Sometimes you might have like something that starts from 10 over 3, and then you subtract 1 is 7 over 3, then 4 over 3. Something like this could happen too, right? So you need something that would handle these cases, and that's why gamma functions are used. Well, the real reason when gamma function was first invented was, I think Stirling wanted to have some approximate value of the factorial. So there's something called Stirling's formula, which gives you the approximate value of the factorial for a really large value of n. And you need that to show some convergence results. But for our purpose, it's really this. Okay. One another thing that's often used and quite amusing is that gamma of 1/2, which is defined as from 0 to infinity, of t to the negative 1/2 e to the negative t dt is equal to square root of pi. Now, why would that be? Now, usually people just mention this, but I actually want to show you a little bit because it deals with something that we've already done. So think about the following. So I'm saying that this is equal to square root of pi. We know something else that gives you square root of pi. Which one is that?
The error coefficient?
Yeah, the e to the negative x squared, right? So I wish that this thing was x squared. What happens then? Well, let's see. If you set t as x squared, then dt is 2x times dx, right? And when t is 0, x is 0, t is infinity, x is infinity as well. So this integration is same as 0 to infinity of t to the, t to the negative 1/2 times e to the negative x squared times 2x. But what is x? X is 1/2 power of t, right? If you take the square root of both sides. So this would be t to the 1/2 power dt. And these two, this is the reciprocal of this one, so they cancel. Right? What is this? Well, you can use double backwards to make it really an integral from negative infinity to infinity of e to the negative x squared dx. That's exactly the error function calculation, right? Yes?
It should be dx.
Oh, so this should be dx. Thank you. Yeah. So this is going to be square root of pi. So that's the result. Gamma of 1/2 is equal to square root of pi because of this calculation. So that actually tells you more about other values. So for example, what's gamma of 3/2? This would be 1/2 times gamma of 1/2, right? What's gamma of 5/2? This is 3/2 times gamma of 3/2, right? But then it will be 3/4 of square root of pi. So you see that gamma of odd over 2 cases all have square root of pi as. Yeah, so the amazing thing about the gamma function is that not only for the integers it gives you the factorials, for numbers that are not integers you have things that behave like factorials. That's the idea.